Okay, let's solve some log equations. Here are three basic examples that move the x in different spots. The x can be here inside the function, it can be here as the base, or it can be over here as the power that the log is equal to. Moving the x into three different spots can change how you solve it, and so you want to be aware of all of these scenarios. Most of these problems can be solved by converting. This is the most common type of problem where the x is here in this parenthesis. It's the log of x plus 4. We want to get that x by itself. If we convert, then we say 3 to the 10th equals x plus 4. X plus 4, not x to the 4th. Well, now we can very easily get that x by itself. We just say 3 to the 10th minus 4 equals x, and we calculate 3 to the 10th. $59,045. And you can check that pretty quickly if you wanted to. Do the change of base formula or do a log base in your calculator. You're going to get 5945. Now, a lot of books show this problem differently. They don't show it by doing converting. They show it with doing what's called exponentiating both sides, which basically means since this is a base of 3, I raise 3 to the power of the two sides. So 3 to the log base of 3 to the x plus 4 equals 3 to the 10. Raise both sides to the power of 3. And then there's that property that kind of lets these things cancel. That's not really what happens, but basically those go away, and you get x plus 4 equals 3 to the 10th. And subtract the 4 from both sides, and you get x equals 3 to the 10th minus 4. And there might be some situations where you want to know how to do that, but in general, most problems can be solved by converting instead of by raising both sides to a power. Next. The x is here. This doesn't happen very often because it's pretty rare that you don't know what base you're dealing with. I can't think of a scenario where you don't know what the base is, but I want to show what happens in case you do. X to the 4th equals 18. Well, this is now a polynomial. That's not exponential because the power is a number, so we'll just take the 4th root of both sides. You find the 4th root of 18. Or 18 to the 1/4 is the same thing. That's 2.06. Now, I should probably say that it could be plus or minus because we did an even root, but you can't actually have a negative base for a log, so it's just going to be 2.06. Here, be really careful. The x is pretty much already by itself. We don't need to do any converting because the x is already over here isolated. Let's just get it a little more isolated. So I'll have to do the change of base formula, log of 25 divided by the log of 2/3, and do that and divided by 2. Log of 25 divided by the log of 2/3 divided by 2, and this is going to be negative 4 basically. So there's having the x in any one of your three positions for log problems, as the base, as the power, or as that function input. From there, you can solve pretty much anything else that comes at you. Like, oftentimes you'll have multiple logs to deal with, and these can involve properties of logs in pretty useful ways. Remember, if nothing is written down here as a base, your base is 10. This is called a common log. Well, logically, if this value, this is just some number, if this value is equal to this value, the only way that's possible is if x plus 3 equals 10. You can really just drop the logs and their bases if you have the same base and just one log on both sides. Again, the way that books would tend to show this is they'd say do this times do 10 to this power and 10 to this power, like literally 10 to the log of x plus 3 equals 10 to the log of 10. And then because these bases match, these cancel, and you'll get x plus 3 equals 10. But logically we know that if this is true, then this must be true, which means that x is going to be 7. Subtract a 3 from both sides. But notice how these problems can be different. This has multiple logs, but only on one side of the equation. This is where you need to have your properties of logs. We have log base 5 of x plus 3 plus log base 5 of x equals negative 2. And there's no way that I can cancel these logs or drop these logs or get rid of the bases or anything. But I do know that addition becomes multiplication. these things multiply when you're adding logs of the same base. Now I can do powers. 5 to the negative 2, I can convert 5 to the negative 2 equals x squared plus 3x. Ooh. This is going to work out way uglier than I thought it was going to, but that's okay. And so we get a quadratic. X squared plus 3x plus 1 over 25. So that's minus 1 over 25. Let's subtract that 1/25 from both sides. And this is way uglier than I thought it was. I thought it was going to come out real clean, and now I feel silly. But we'll solve it anyways. It's just a quadratic, so I'll do the quadratic formula. Parentheses negative b plus the square root of b squared minus 4 times a times c divided by 2a. There's one of my ugly answers. Changes plus to a minus. There's my other ugly answers. My options are x could be 0.005 or x could be negative 1.2. 0.21 really. And we have to remember that you can't take a log of a negative number. This happens most of the time when you have quadratics. You can't take the log of a negative number, so that solution's not going to work. Like, if I did log base 5, I'll do like an easy example, negative 25 even. Well, this doesn't equal anything. There's 5 to no power can equal negative 25, because 5 to any power will always be positive. Even 5 to a negative power is still a positive number, because 5 to the negative 2 isn't negative 25, 5 to the negative 2 is 1/25. So when you have quadratics, you get two solutions. Usually, only one of them works. Let's get to this one. Here's our final example. Notice this is just some number. Some number that I could calculate, I could find. This is also just some number, but I don't know what that number is because there's an x in it. But because that's just some number, if I wanted to, I could just calculate what that number is. Log 11 divided by log 4. Change of base formula. That's number 1.73. So I can solve a little bit. Add or subtract the 1.73 from both sides, and I get 12.27. Divide both sides by negative 1. And then 4 to the negative 12.27 power equals x. And x is going to be 4.1 times 10 to the negative 8. Very silly answer, but certainly a possible one. Now that's not the only way to do this, but it's just worth recognizing this is just some number. Treat it like it's some number. Another great way to handle this is that subtraction actually becomes division. So I could do log base 4 of 11 over x equals 14. Then do 4 to the 14th divided by 11. Why does that seem so different? Awkward silence. Ah, okay, it's not at all different. It's actually the same. I just got to finish. I'm going to take this and come down here. To solve this, it has an x on the bottom, so it becomes a really big number, turns into a really small number. We're going to get 4 to the 14th equals 11 over x. And then to solve that, I'd multiply both sides by x. And divide both sides by 4 to the 14th. And this is going to be the same as this. So the adding and subtracting properties become important when you need to combine multiple logs. It only works if you have the same base, but typically you do. If you don't, there's tricks you can pull to get the same base, but we won't worry about that. Thank you.